Hello. So now it is time for us to talk about one of the more critical chapters of this course, which is optimization and how do we apply it in civil engineering. In civil engineering, we use optimization to make smart, efficient decisions under constraints, and we always have constraints: budget, time, you know, volume, area. All these things are constraints for us, spans as well. So, in this lecture, we will introduce the core principles and summarize them of continuous and discrete optimization. And we will look at knapsack problems, which is one of the most used models when we're talking about optimization. So, optimization is essentially the art of decision making, the art and science of decision making. And when we say science, because math is a big part of it. So in civil engineering, we're constantly faced with trade-offs. I need more of this, less of that, and so on and so forth. Budget limits, space limitations, environmental concerns, you name it. So optimization helps us find the best solution that satisfies all of these constraints. This might mean minimizing cost, maximizing performance, and balancing both. So multiple objectives. Optimization is everywhere in civil engineering. We use it during planning to choose the best project sequence. We use it during design to pick the right materials and dimensions. We use it during construction to allocate resources efficiently, so which machine goes where. We do it during maintenance to schedule inspections and repairs at the right time. And in end of life, to decide when and how to decommission or recycle an infrastructure. No matter the project phase, we're always trying to get the most value from limited resources. There are two broad categories of optimization problems. Continuous optimization, which deals with variables that can take any real value, so decimals, right? Like the exact quantity of concrete or reinforcement. And we have discrete optimization on the other hand. It involves variables that take on specific values, often binary. Binary is the most common form of discrete optimization. Or integers, 1, 2, 3, 4, like high, medium, low, and stuff like that. Such as whether to fund a specific bridge repair this year or not. So 0 is no and 1 is yes. You can't have a third option. There is no maybe. Like I will maybe fund it. I will give 50% of the money. That's illogical. So let's look at both more closely. In continuous optimization, the decision variables form a spectrum. Think of adjusting the height of a dam, right? You can change it by millimeters if you want. Or the thickness of a pavement layer. Same thing applies. You can fine-tune these values, find, the best. On the small scale, you can find the best fit. Linear programming is one of the most widely used tools here. So the graphs we have drawn in class, this is like part of 2D linear programming or solving a 2D problem. The feasible region is often a polygon in 2D or a polyhedron in higher dimensions, 3D and more, but we haven't solved something like that yet. And the goal is to find the optimal point on its boundary, and it's usually one of the vertices. Discrete optimization problems deal with indivisible choices. You cannot divide, I want 15 trucks and a half. Which half? The motor or without the motor? Catch my point? So, discrete optimization problems deal with indivisible choices. Should we upgrade the system? Yes or no? Should we assign 3 or 4 workers to this task? There is no 3.5. These problems are harder to solve than continuous ones because the solution space is not smooth. It's not easy to draw, right? So you can't just take derivatives and move infinitesimally like in continuous. One famous discrete problem is the knapsack problem. Either I take the item or not because I have a specific volume I need to put it in my bag. Imagine you have a limited capacity backpack and a bunch of items, each with a value and a weight. You want to pack it with the most valuable combination of items without exceeding the weight limit. In civil engineering, the knapsack metaphor helps us with resource allocation specifically, selecting the most beneficial set of projects, materials, or actions within our budget. So if I'm going to take on a specific project, I need to take on the whole project. I will not take on half a project. Catch my point? This image here helps us identify the different types of goals in a knapsack problem, right? So it is either total reward maximization. So from my choices, the total reward, I want to make it as high as possible. Or if I'm selecting an X number of item, I want the solution with the highest possible average per reward. Average per reward. And this can be said to cost. Either I want the maximum total cost or the minimum total cost, or the maximum average cost or the minimum average cost per item. One other approach is also benefit to cost ratio. I want the maximum benefit to cost ratio or the maximum average benefit to cost ratio. So, and remember, benefit to cost can become cost over benefit. So we can switch that. So, knapsack problems also are divided into certain variants. We have multi-dimensional knapsack, which means it has multiple constraints. I am optimizing on multiple levels, multiple dimensions. I am optimizing on multiple dimensions. And we have multi-choice knapsack, which is selecting one option will have multiple categories, as in the figure here. Like I have certain options and each one of them, not all of them, but the green, the blue, and the yellow has multiple choices. So I have A, B, and C within the choice itself. So when rewards and costs are uncertain in general systems, we can also have multi-choice, multi-dimensional knapsacks, as in both of these come together. We would have a lot of dimensions with optimizing on multiple fronts, and each one of these options choices has multiple options. So you're on multiple levels. It's like a tree within a tree. It's a lot, and it's very demanding computationally. So we'll move on from here now to solving a 2D optimization problem by hand. Okay, so we want to solve an optimization problem that looks like this. I want to max my goal function z equals to 6x plus 4y. Subject to, and pay attention to how do we write our function. Subject to 3x plus 2y less than or equal to 30, 2x plus 4y less than or equal to 32, x greater than or equal to 2, and the non-negativity x greater than or equal to 0 and y greater than or equal to 0. Of course, again, this does not always apply. It really depends if it is logical for your problem to have a negative solution or not. For example, we're talking here, the example is about amount of cement and sand. right? You can't have a negative amount of cement and a negative amount of sand in mixed design. That is just simply not logical, right? So first, we want to draw these constraints. So I set up my x-axis, I set up my y-axis, and this is going to be near approximate because I don't have, the grid lines established. So we will try to the best of our ability to have something feasible and logical here. So, first thing first, I think it is always the best way to start is with the constant lines. So we have 0 here, we have 1 and 2, and this is x prime or x. So this is the x, and this is my 1. So this is 1, and this is 2, right? So I draw a straight line here. Apologies for that. I don't know if there's a snap option really to make things look in different color. Let me see. Oh yeah, we can change the color. Okay, so we have x greater than 2, and since it is greater, which means this is the feasible region, and this I no longer want to use. So I scratch it away. This is not feasible now. This is gone. Now I have 3x plus 2y less than or equal to 30 and 2x plus 4y less than or equal to 32. So let's deal with the first one, 3x plus 2y and equal to 30. Why? Because this is the boundary line. So we replace the inequality with an equality. So let x equals 0. If x is equal to 0, 2y is equal to 30. This means y equals 15. So my first point is 0, 15. And then let y equals 0. We get 3x equals 30. This means x equals 10. So my second point is 10, 0. So it is somewhere here. Let's call the 10 and put the 30 the 15 all the way. And then let's connect with let's use green here and try to connect them. It's not gonna be perfect. I'm using my hand. So this is 3x plus 2y. So we need to figure out the direction. We take the x over there, so y is less than. So this means I'm going downwards. So what do? I scratch the area above, right? So now my feasible region is narrowing down. Now, next up, we have 2x plus 4y less than or equal to 32. So 2x plus 4y equals 32 because this is the boundary line. And let x equals 0, so 4y equals 32. So it is 0, 8. 32 over 4 is 8. Let y equals 0. So x will be equal to 16. So 0, 16. So we have, 16, 0. Why isn't it erasing? It is not. 16, 0. 16, 0. So we have 16, 0, which is way farther back. Almost, let's say it is here. And the other point is 0, 8, which is almost here. And we want to connect them together. We go something like this. So we have now 4y. We have 4y less than or equal to 32 minus 2x. So it is also less than. So this eliminates this area as well for me. And now what is my feasible region? This is my feasible region here. Let's change the color. Go with orange. So now this is my feasible region, right? This is gone as well, because this is gone by 3x plus 2y. So I have 4 vertices now, 4 feasible options. I need to get their coordinates. This one I already know, by the way. The one on the x-axis, which is 10, 0. This one I know. And this one has x equals 2. X equals 2, and that's y is 0. So also this one is 2, 0. Right? So I got my first 2. Now I have this one here. This one here is the intersection between x equals 2 and 3x plus 2y. So we have 3x plus 2y at x equals 2 is equal to what? Is equal to 30. So y equals 30 minus 3x over 2. So 3 times 2 is 6. 30 minus 6 is 24 over 2. So y is equal to 12. So this one is 212. Right? And then we have this final one. And to solve such an intersection, there is really only one way to do it, which is y equals y. So we need to convert these two to their y form and find the intersection. Okay? So let me erase here a bit. And go back to writing. Okay. It's not writing for some reason. Huh? Okay. Okay, we're having technical difficulties now. It's refusing to write. Okay, we're back. So we have 3x plus 2y equal to 30. This means that y is equal to 30 minus 3x over 2, which is equal to 15 minus 1.5x. And the other one is 2x plus 4y. 2x plus 4y equals 32, which implies y equals 32 minus 2x over 4, which is 8 minus 0.5x. Let's erase again. Oh, that just happened. Erase. Okay. No, great. So 8 minus 0.5x is equal to 15 minus 1.5x. So we get, let's take the 1.5 to this side and the 8 to the other side. We get x is equal to 15 minus 8, which is 7. Now we replace the 7 in one of those equations. So y equals 8 minus 0.5x, which means 8 minus 3.5, you get 4.5. So this point right here is 7, 4.5. Now what do? I have all my vertices. I replace them into my max function. So 6x plus 4y, we have option 1, option 2, option 3, and option 4. And we get their values. So option 1 is 6x plus 4 times 0. So we're doing this one here. So the result is 12. The other option is this one here, option 2, which is 6 times 10 plus 0, which is 60. And option 3 is 6 times 12 plus 4 times 6 times 2, which is 12, plus 4 times 12, which is 48. So 12 plus 48, you get 60 again. And then you have 6 times 7, which is 42, plus 4 times 4.5, which is 18. So guess what? It is 60 as well. So my goal is to max, right? This is a 60, this is a 60, and this is a 60. So I have 3 feasible solutions, and that's completely fine. So we are okay with this. We are happy with this, to have 3 possible solutions. It's very good. And then I have the option to choose between them based on other factors as well. So that's how you would solve generally a 2D optimization problem. Practice as much as possible and get good at it, quick at it. Always remember, if I want to solve an intersection, it is y equals y. Okay, best of luck.